Will putting the stream up there also kill the internet if I have it streaming the other machine? I'll let it stream on the other machine just so we can see what they see and see if there's any technical.
Alrighty, we're back. Wonderful, nice.
We don't appear to be.
Oh, that's just that computer.
Oh, alright. Okay. Sure, I trust you. Alright. So, where were we? Alright, so we're trying to write a piece of code. It takes the maximum of 3 arguments. So I've split it into 2 pieces. Take the maximum of the first 2 arguments, and then whatever that is, I'll then take the maximum of that with the third argument. So we've got R0, R1, R2. And the first thing I want to do is take the maximum of R0 and R1 and store the result in some dummy register R3. So I do the comparison. And then if the negative flag is set, that means, well, when would the result of this subtraction be negative? When R0 is bigger. So we can go branch on negative, which I have to read my cheat sheet to read what that is. That's a BMI. BMI for branch minus. Now branch minus to max 1, I don't know, R0 bigger. So, and then otherwise, R1 is the bigger one. So max 1, R1 big. Max 1, R0 big. So if we do the subtraction and the result was negative, that means R0 is the bigger one. So we'll branch on a negative down to here. If R0 is the bigger one, then we move R0 into R3 as like a temporary measure. Alright, so R3 is just temporarily remembering which one's the bigger one. And so if that wasn't the case, then what I want to do is I want to move R1 into R3 because R1 was the bigger one. R1 is, so when would I jump down here? When R0 is strictly bigger. And I would be here if R1 is bigger than or equal to R0. There we go. So far, so good. Then I want to go to max 2 and do the same thing again. But if I execute this piece of code here, I'll immediately jump down to this piece of code. So I need to put a branch that sort of skips out of that loop. So maybe we'll do that in a different color. I need to put a B max 2 and sort of sneak that in here, in between those 2 instructions. Okay, now we're at max 2. So I'll put a little comment here just to remind me. R3 now contains the maximum of R0 and R1. And essentially what I'm going to do is I'm going to do the exact same thing again. I'm going to test which between R2 and R3 is bigger, and then put the bigger number in R0. So I do another compare. So I compare R2 to R3. If the negative flag was set, that means this number here, the number stored in R3, is the bigger number. So, and I'm running out of room here, so I'm going to destroy my pseudocode. If you want to have a look at it again, you can always, I guess, rewind the stream and it will be there. So I'll put a little line there. All right. Compare R2 to R3, and if R3 is the bigger one, the negative flag will be set. So I'll branch on a minus to max 2 R3 bigger. All right, and then this code will continue up here. So like just imagine this stuff here is directly below here. So we have max 2 R3 is bigger, and we have max 2 R2 bigger. All right, my naming convention for my labels could probably use a little bit of work, but that's okay. Hey John, can you just keep an eye on the chat? I can't read it.
Yeah, I'm answering chat.
Oh, too easy. All right. So if R2 is the bigger one, we want to put R2 in R0, because R0 is our output that we've agreed on. And then I guess branch to end. And if R3 was the bigger one, I will move R3 into R0. And then I'll fall into end anyway. And then end is the usual, not branch to end, which just represents that the code's finished. There we go. I guess we can test this. I can like execute this by hand. So I will have my registers here. R0, R1, R2, R3. And I'll just use my finger as the program counter, so it'll indicate where we're up to. So start in main, and all my registers have unknown rubbish inside. Move a 4 into R0. All right, so we'll put a 4 here. Move a 1 into, move a 7 into R1. 7 goes here. Move a 5 into R2. And after all this code is executed, hopefully R0 will contain 7, because 7 is the bigger number of 1 and 5, of 4 and 5 and 7. So 7 is the biggest number, so hopefully this thing ends up in R0. So take R1, which contains 7, and subtract R0, which contains a 4. 7 take 4 is equal to 3, which means the negative flag will not be set. And then we don't store the subtraction anywhere, we just do the subtraction and set the flag. So maybe I should also have something to represent my negative flag. So I'll put an N here. 7 take 4 is 3. 3 is positive, so the negative flag is set to 0. Alright. If the negative flag is set to 1, branch to R0 big, so we're not going to do that, which means I just fall through and execute the next instruction. Move R1 into R3. So take the value in R1, copy it into R3. So now R3 contains a 7. Alright, and the next instruction, I had to sort of sneak it in because I forgot to put it there. Branch to max 2. So I go whoop and jump all the way over here to max 2. What's the next thing I'm going to be doing? Compare R2 to R3. So essentially, take R2 and subtract R3. R2, subtract R3. 5 takes 7 is negative 2. Negative 2 is unsurprisingly negative, so we set the negative flag. So the negative flag gets set, so put a bit 1 there to represent that. And then we go to the next command. If the negative flag is set, which it is, because we just set it, branch to this label here. So we will go to max 2 R3 big, which will go jump over here, and then we execute this piece of code. Move R3 into R0. So take the 7 and put it in R0, and then get stuck in an infinite loop. Cool. The R0 register contains 7, and 7 is the biggest number out of 4 and 5 and 7. So it looks like our code works, at least for the case where R1 is the biggest. It's probably worth testing them for the other cases. I will leave that as an exercise to you, but this is how we do it. And there's many different ways to solve this problem. The messy solution would be to do each of the possible comparisons, which I guess would be a truckload to do, especially if there's like more and more numbers. But the way I'm doing it is I just take, so suppose we had like more numbers to compare. So suppose I had like 4 numbers in a row. 1, 9, 3, 6. What I do is I compare the first two. 9 is bigger. And then maybe I'll put the 9 elsewhere so I don't get it immediately. So I'll make that 7 and make this a 4, make this a 7, make that a 6. Okay, cool. So, that's out of frame. Let me sort of scoot back a little bit. There we go. So suppose we had like more numbers and I wanted to take the maximum of these. The same algorithm I did before generalizes. So you compare the first two. 4 is bigger, so you hide the 4 somewhere. You then compare the next number to the hidden away number. 7 is bigger, so I'll remember a 7. Compare the next number 6 to the 7. 7 is still bigger, so then we return 7. And it's important you have this little temporary space to remember the biggest number you've seen so far. Because if you just go through and compare adjacent digits, well, the biggest number might be at the start, and then you might forget it afterwards. So this is one way to compute the maximum of a collection of numbers. And this algorithm will take linear time. For n numbers, it's going to take n comparisons to find the biggest number. Does anyone any questions in the chat about that, John?
Anyone have any questions about what we're doing right here? Sorry, I'm just answering a billion questions in chat.
Oh, that's all right.
Now, Dave, do you know what resources students will get in the midsem? So I know they'll get the assembly cheat sheet. How about, say, the hexadecimal binary converter widget, reference manual? Do we?
All right. So to the best of my knowledge, I don't know for certain because it should say on the website, but you will be getting the cheat sheet. And you will not have access to the internet, which means you probably won't be able to get to your hexadecimal binary conversion widget. Because you won't have internet access, right? Do you want to swap, John? You can do whiteboard. I can answer chat for a bit.
Yeah. So actually, yeah. If you go on over there, you should be able to still see the chat, and you can.
Okay, sure. So I'll tap out here, and then you can jump in.
Yeah,
And
cool.
you can jump
Alrighty. Also, if you can make a quick list of all the different questions people are asking in chat, that'd be wonderful. We got a few requests.
All right. Let me just go back and read it all.
Alrighty. We should now be looking at my desktop. I'll spin the camera around so you can look at my wonderful face. Oh, hello everyone. Welcome to the live stream. G'day.
The camera's upside down, John.
No, it's not. It's the right way up.
Oh, okay, sure.
Cool EO. So, what's everyone asking me to do? Okay, what was the first request?
Rundown on flags. It looks like a couple of people want.
Quick rundown on flags. Oh, okay, well, poo. That's slightly easier to do on a whiteboard. Okay, well.
We'll just up on the whiteboard then.
Flaggies.
That's definitely a thing to do on the whiteboard.
Yeah. Okay. Let me switch this back to whiteboard mode then. Document camera, transition, ka-chow, bang, cool. Alright. Excuse me, fellas, let me spin it around. Hello. Woo, hee.
And so you can just flip the board over, just in case we ever want to show that part again.
Yeah, snap.
More room on the other side.
No, there isn't.
No, there isn't. Alright, well, I guess if you want to see it again, you can rewind, so just rub it out.
Okay, buddy, last chance opportunity. 5, 4, 3, 2, 1, goodbye.
Yeah. I'm honestly going to go to rapid fire answer all these questions.
Yep. Have you logged in? Yeah, cool.
Yeah.
Alright.
Stuff on functions and stack pointers, maybe.
Yeah. So I'm sorry this stream isn't particularly well organized. This was an idea that Dave and I had last night when we finished up doing a whole bunch of videos. Hopefully in the future we'll be able to do things in a slightly more organized and nice way. Alright, so flags. Flags are special bits in our status register that the CPU can set to tell us the result of an instruction in ways that we might not be able to sort of immediately work out from the kind of mathematical result. So what flags do we have? We have the Z flag, which is 0. Cool, that's coming out okay, wonderful. What other flags do we have? We have the carry flag, which is C. The overflow flag, which is V. And what am I missing here? 0, carry, overflow, and Dave. What am I missing? What's going
on? 0, carry, overflow, negative.
Negative.
There's a couple of more flags, but we don't really care about them. These are the only 4 that we care about.
Okay, so the way that flags work in general, if we do an operation, say an add s instruction, and the result has one of these conditions, it will set that flag to a 1, and all of the other flags will be cleared to 0. Now, it's very important to remember that most instructions will not set flags unless you explicitly tell them to. So when we do an add instruction, we need to have this little s on the end here. Think of the s as stands for setting flags. Okay, so let's think of a few different situations where we might set flags.
Do bit shifts and masking next, I think.
Yeah, okay. So I'm going to work on a pretend 4-bit computer because 4 bits is really quick to write on the whiteboard. So let's do an add of two numbers here and see what we get. Yep, there we go. Boom. Alright, so this is going to be my little add over here. Now let's add, say, 1, 1, 0, 0, and what can I add to this to make things happen? Well, let me think about this for a minute. I gotta make sure I'm not doing anything silly. 1, 1, 1. Alright, now if we were to convert these to decimal real quick, that'll be a 1, 2, 4 plus 8, that'll be a 12. Let me write in different colors. So, sorry, that'll be a decimal 12, and then we have a decimal 12, and the bottom number is going to be a decimal 1 plus 2, 3 plus 4, 7. Yep, 7. Cool. Okay, now what happens when we add these? So remembering that the biggest number we can represent here is 15. So if we do this in decimal, we'll have 12 plus 7. That's going to be 19. That's going to wrap around. So 19 minus 15, that's going to be 4, I think, afterwards. Let's do our binary addition and see what we get. So 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 1, and we carry the 1. Oh, I'll use pink for carry up here. Oop. And then we have 1 plus 0 plus 1, which is 1 carry 1. Cool, okay. Yeah, have I done that right?
What have you done? 12,
oh, sorry,
12 plus 7?
That should be a 0, I think.
0 plus 1 is 1. 1 plus 0 plus 1 is 1. 1 plus 1 is 0, carry the 1.
Yeah.
So you should put a little thing for a carry, perhaps.
Yeah, so I've got the little pink...
the pink thing for a carry.
Carry bit.
And then 1 plus 0 plus 1 plus 1 is 1, carry the 1, and that 1 falls off the end of the world into the carried bit slot.
Okay, cool.
So put another little box there in a different colour, because that'll be the carried bit slot.
Okay, so...
Lots of different colours.
Alright.
There we go.
Here's the first flag which we set, which wasn't the one I wanted to demonstrate, but here we are. So, alright, so we've done this addition, right? So these two, this all adds, right? And every time we've had to sort of carry a bit over, I put a little 1 here. Because if we do 1 plus 1 in binary, we don't actually have like a 2 character. So we just put a 0 and then put a 1 in the next significant bit up. So when we do it in the last column, we've actually carried a bit over off the end of our imaginary little 4-bit register here. So this bit then goes into the carry register. So after this instruction, our flags would be, well, would the Z flag be set? No, because this number is not 0. Would the carry flag be set? Yes, because we have carried a bit out. So that's this bit here, the carry flag here. Would this be an overflow? Ooh, would this be an overflow?
So when does an overflow flow caused again?
When we go from... It's when we change the most significant bit, yeah?
Yes, it's when we go from a really, really big positive number, like in 4-bit land 7, to a really, really negative number, like -8. That's when overflows happen.
So I don't think this would set overflow then.
Well, you have, right? Because you've got 12 plus 7. 12 plus 7 is 13, 14, 15. 16. 16 is too big, so I go back to 0, right? Oh no, that's a carry. What am I talking about? Yeah.
Overflow, because this...
That's carry.
If this was 2's complement, this would be a negative number. Pretty sure overflow is not set.
No. If this 1011, that's a negative number. Right? The problem is you shouldn't ever talk about overflow unless you're talking about negative numbers, right? So maybe talk about carrying that one and do a separate example.
Yeah. Okay. So. Yeah, I'm gonna. I can't remember what the overflow is going to be after this. Let's not worry about it. We're talking about unsigned numbers here, so we don't actually want to really care about the overflow. It's not really meaningful to us. And now finally, also negative. Negative is very easy because negative is 1. Negative is just the most significant bit of the output. So negatives are real easy to pick up on one. If we were representing this as a signed number, then this would be a negative result. It would be negative what? What would that be?
What universe is that a 4? If you're talking about unsigned, that's going to be 8 plus 4 plus 2 plus 1.
Yeah, I
9, 10, 11. That's 11, John.
Yeah, I goofball my math.
Yeah.
Okay, cool. So that was a really spaghetti droppy introduction to some carry flags. We got there eventually, and we didn't even work out what the overflow was. Hooray! Wonderful. Let's do a slightly better example. Hopefully, I'll try not to drop the spaghetti so hard. All right. Let's do a really nice, simple addition. One that will give us a 0 flag. Okay, so here's a much better demonstration of carry and 0. let's add these two numbers together. All right, so 1 plus 1 is going to be 0, and we'll carry the 1. 1 plus 0 plus 1 is going to be 0, carry the 1, and so on and so forth. And we'll have our 1 in here, and 1 plus 0 plus 1, carry the 1 again. Oh, wrong color. Okay, cool. Now 1 plus 0 plus 1 is going to be, 0 again, and we'll also carry out a 1. Okay, here's a much nicer demonstration of the carry. Okay, so I can confidently say here that 0, 0, 0, 0 is a 0 number, so the Z flag will be set. Carry will be set because we carried a bit out. Overflow will not be set in this case, I don't believe, and negative will be not set as well. So we can say a flag is not set, or we can say a flag is cleared. In either case, we're talking about the flag being equal to 0. Okay, cool. Now let's just keep using adds for now, because adds are nice and simple to think about, and we can do them very quickly and easily over here. All right. Oh no, that last one would have set overflow, I think. No, sorry, it wouldn't have. Ignore me. All right, let's do one that sets overflow. Okay, here's a nice, easy overflow setting one. So let's work out what these numbers are. And so now we're going to treat all of these numbers as two signed numbers, which means they can be positive or negative. So what do we have here? In two's complement land or signed number land, we have 1 plus 2 plus 4, we have 7. And we have a 1 down here. So these are still just positive numbers, but some wacky things are going to happen when we add them together. So we'll do our addition. 1 plus 1, it's going to be 0.
But before you do that, maybe it's worth quickly doing a recap on what two's complement actually is. Like, how do you get a 7 from that bit pattern?
A 7 from this?
I mean, you must 1 plus 2 plus 4, but if there's a 1 at the start, how do you convert it? So the whole flip them all and add 1. Maybe it's just quickly do an example of that first, I think.
Oh, sure. So if we want to get like a negative 7?
Yeah.
Okay. So we flip them all out.
If you don't know what two's complement is, this example is going to make no sense, right?
Okay, cool. So yeah, let's have a quick look at two's complement. And then
we'll come back to this problem.
As Dave said, to convert from a positive number to a negative number in two's complement, we flip all the bits and add 1. How two's complement works essentially is we reserve the top bit here as the sign bit. So if the top bit is 1, the number is negative. If the top bit is 0, the number is positive. So what this looks like then in 4-bit land, this can mean two different things. This can either be positive 15 or it can be negative 1. All right, is that looking okay? Wonderful. Yeah. Okay, cool. Now let's say that we want to, let's say we know how to write positive 7 in binary, so that's what we have over here. And now 1, 1, 1. How do we work out then what negative 7 is going to be in two's complement land? So as Dave said, we just flip all the bits. 1, 0, 0, 0, and then we add 1. So we'll make this a 1. Draw a little box around it to keep it all neat. Okay, cool. And now we have in signed number land, this is a negative 7. And in unsigned number land, this would be a 9.
Maybe put like commas between them so it doesn't look like 9 takes 7.
Nope.
Yeah. So the idea is whenever we have a number and we want to find out how to represent the negative of that number in two, so suppose I want to represent -3, I just write the bit pattern for 3, which is 0, 0, 1, 1.
What do you need?
The bit pattern for 3.
0, 0, 1, 1.
And if I want -3, do the exact same thing we did before. So you flip all the bits, which is 1, 1, 0, 0. and you add 1 to the result. 1, 1, 0, 1. In 4-bit land, that's what -3 looks like. So how does the computer know whether something is signed or unsigned? Definitionally, it can't. It just does the addition. The whole point is that the computer can't do subtraction. We trick it into doing subtraction by interpreting this number as negative and then adding a negative number. Because if we can't do 3 subtract 1, we can trick the computer into doing it by doing 3 plus -1. If you have a look in the glossary, which I've linked in the chat, I've got a little explanation way down the bottom about signed numbers, and that may help. Not to derail you, John.
Yep, that's fine. So, and the reason why we use 2's complement is that if you add under 2's complement a positive and a negative number together, it sort of behaves in the way you would expect it to, right? So, say, let's do a quick sample addition down here. Okay, do I have enough board space for 3 more registers? I do, okay. Alright, so what we're going to do is we're going to add the number 1, let's add 5 and -3. So this is going to be 5.
Before we do it, hopefully the result should be 2, because 5 take 3 is 2, right?
Yeah.
So that's the result we're expecting.
And so hopefully we're going to get this, right? Let's do this now. So 1 plus 1 is 0, and we carry 1. 0 plus 0 plus 1 is 1. 1 plus 1 is 0, we carry a 1. And 1 plus 1 is 0, and a 1 gets carried out. Cool. And now what result do we have in our register down here? 2. We do have 2. Oh no. 2. So just to keep things consistent, -3 or 13. Cool, okay. So yeah, this is why we use 2's complement. Things sort of behave in a way that, you know, we expect them to when we're doing like normal decimal math operations. Okay, that was a really big detour from doing flags, but if anyone was confused, I really do hope that's cleared things up for you. Okay, let me clean off my board a little bit, and we'll go back to talking flags. Okay. So just to recap on a couple of flags, I'm going to cheat a little bit and just use a mov instruction. So mov can set flags, guys. Mov can set flags. Oh god, my handwriting is appalling. Excuse me. Okay, MOVS. Don't mind this like terrible S. Now if I mov all zeros into a register, what flags is this going to set? 0 will be set because this is 0, and none of these will be set because mov doesn't actually set the carry flag or the overflow flag. Okay. Oh, so that's a quick gotcha with flags as well. Not all the instructions set all of the flags, so mov will only set 0 and negative. It won't touch carry and overflow. So it won't even clear these. It will just leave them how they were. So that can be a good gotcha. If you've done an add that has set these flags and in your mov, these flags will still be set from this add instruction, not from the mov. Because mov does not touch these flags.
Unless you put an S on it.
No, mov-s does not, sorry, mov-s does not touch these two flags.
Yes, yeah. And you can tell that by looking at the cheat sheet. On the right-hand side in the column of the cheat sheet, which will look kind of yucky on the camera, there's a big column that
Can you switch to the OBS window?
Yep.
Yep. Okay, yeah, okay, so this column on the cheat sheet shows what flags the instruction will set. And if we look down here, you can sort...
It's not focusing very well.
Yeah. Okay, mov is just where my thumb is, and it's just N and Z. Most of them set N, Z, C, and V, which is what we've got down here. Okay, geez. If we mov 0 in, we'll set 0, and we'll clear negative, and we won't touch C and V. Now, if we mov any negative number, which, if we remember, is any number where the most significant bit is 1. So I'll actually draw question marks in here because we don't care what these bits are. So this will always set negative. This will always set 0. Okay, now I think we were pretty clear earlier about what happens, how we get the carry flag to be set. That's just when we do an add and we don't have enough bits to fit our number in, so we sort of carry a bit out when we're doing our sort of bit by bit addition. Let's look at overflow. All right. So I'll clear out my little add down here and we'll do an overflow.
I don't know if there's a Q flag.
What's the Q flag? I don't know.
Never heard of such a thing. No, you don't need to know what it is.
Yeah.
Oh yeah, there's a. Oh yeah. So when you do a saturated add, there's a flag to indicate the result got saturated. That's what I'm guessing.
Okay.
Yeah.
We don't need to know about saturation.
We don't need to know about saturated adds. So no, who cares?
Oh yeah. So here's our final flag setting example that I'm going to do for you, unless anyone else has any further requests. So what this is going to set now is, what we're going to look at is the overflow flag specifically. So as usual, we'll do our addition here. Rah-de-rah-de-rah. 0 carry to 1. 1 0 1, which is going to be 0 carry to 1. 0 carry to 1. 0 0 1 1. Okay. Now, if you remember in our 2's complement explanation we just gave, the top bit is reserved for the sign bit. So this bit tells us if the number is a positive or a negative in 2's complement land. So let's fill out all our other flags first. So Z, C, and N. Actually, no, sorry, I'll keep them in the same order. B and N. Okay. So, is this number 0? No, 0 flag will be cleared. Did we carry a bit out doing our addition? No. The last bit we carried went into this bit here. We did 0 plus 1, which is just 1. We didn't have to carry out, so carry is not set. Now, overflow. Did we set overflow? And the answer is yes. So the reason why we set overflow, when we're representing positive numbers in 2's complement, we cannot use the top bit. So we've taken the number 7 up here, and we've added the number 1. Now, what we would expect to get in unsigned land is 8. But if we were representing numbers in 2's complement right now, what we would actually have is negative 8. So basically, overflow is what gets set if we add 2 positive numbers and get a negative number out in signed number land. So you can think of it, we have 2 inputs which have the negative flag, the negative bit as 0, and the output had it as a 1. So we've set overflow. We use this flag so, because you would expect 7 plus 1 to equal 8, but in this case it didn't equal 8. This flag tells us why. And now finally, we're going to see, did we set the negative flag? Yes, because the most significant bit is a 1, which means in 2's complement land, this is a negative number. Okay, coolio. I'm just going to hold this up a tiny bit if you want to take a photo of it, or pause the video, or whatever. Cool, okay, I hope that was informative on flags. Anything in the chat?
Yeah, I'm going to do a few examples on load twiddle store and the bit masking stuff. So I'll do the example with the light bulb and the dynamite that I did last time.
Okay, coolio.
Because that's a cute example.
We erase for you.
Alright, so you can handle the chat and I'll handle the whiteboard again, and we can just like tap in and out. Oh!
Oppa!
I lost the camera.
Okay.
Well, there it goes.
Oh.
Alright, cool. Alright. Me again. So I'm going to go through an example of load twiddle store and how to modify particular bits in a register. So first off, what is load twiddle store? So load twiddle, which is a funny word, and store. So the idea is I've got some stuff in memory. I can't touch the stuff in memory. If I want to add a number to it, I can't do that. The only way I can modify memory is I load something into a register. That's the load part. I twiddle, I do stuff with the register, and then I store it back to memory. So suppose we've got a under the data section, so dot data, and I've got a label called John's age. How old are you, John?
20.
20, all right. So we'll put dot byte 20, and maybe it's John's birthday, so we want to like load John's age from memory and then add 1 to it.
It's my birthday this Saturday. Shit, yeah.
Well, there you go. All right. So I'll have a label John's b-day. What we want to do is we want to load this piece of data. We want to make this number 1 bigger. So the first thing we have to do, I need to load, but I don't know where to load from. So I need to take the address of where this information is stored, which is represented by the label John's age, and put that into a register. So what do? I execute LDR, some register, and then equal John's age. And we'll play, as we're playing along at home, we'll sort of write what the register does. So what that will do is it will take some great big number that represents where this data lives in memory, not the data itself, and store it into R0. So you can imagine by analogy, you have like a whole bunch of little mailboxes. So here's my little mailbox. Mailboxes on a street. One of these mailboxes has got John's age inside, and each of these mailboxes has like an address. So the address of this one is OX200, OX201, maybe there's got some other number in it. So what we're going to do here, by executing this command, we load the address of where the data lives, not the data itself. So R0 will contain some yucky big number, probably OX2 bajillion, because this is the first bit of information in the data section. So R0 now contains where it lives. I now want to load that data itself. So, John, can you switch to OBS just so I can see where the whiteboard is?
Yep.
Yep, cool, all right, thank you. We got the address. I now want the data. So I'll do LDR R1 where R0 points. And this square brackets essentially means fetch from memory. From memory. So the effect of that instruction is R1 will contain the data loaded from R0. Now I've got to be careful here because this only takes up a single byte. You know what, I'll just change it to a word for now. We'll talk about bytes later. So I'll change this to a word. There we go. So this piece of information is taking up 4 bytes. And it's going to be stored as, I don't know, what's 20 when you convert it from decimal to hexadecimal? It's 16 plus 4, so it's 1, 4?
Yeah, that sounds right.
Yep. So R1 will contain 00000014, which is John's age in hexadecimal. I've done the load part, so that's done. I now want to do the, oh, that's annoying, that light. I'm going to shift back a bit. There we go. I'm now going to do the, it's a little too far. That'll do. Right, so I'm now going to do the twiddle, where I take the, do you want to kill that light?
What I'll actually do is I'll just move the camera towards it.
Oh yeah, that's better. And let's just move that hotspot. If you turn that light's not very illuminating, if you just turn it off, does it make much of a difference? Oh yeah, that's a lot more.
That's fine.
Oh yeah, that's alright.
Sorry, difficulties.
That's alright. Okay, so we've done the load. I now want to do the twiddle. So John's age is currently stored in R1, so I'm gonna add 1 to it. Add R1 1, which will turn this into OX15. And then I want to store that back. So I go str for store the data in R1 back into where R0 points, which will take this number and copy it back to where we got it, overriding this with a number that's 1 bigger. So this part here is the load. This part here is the twiddle. And this part here is the store. Okay? And I guess this part here is like setting up the address, which doesn't really have a nice name. I guess it's like, it's part of the load, right? So we set up the address in some register. We fetch the data from that address. We do whatever we want to do with the data. And then we put it back afterwards. I can't read from here. John, can you have a look at their chat?
Yeah.
Hope everybody's happy with that.
Yeah.
Cool. Alright. So what was the next thing I promised I'd do? Bit masking stuff.
Right,
Yeah.
So so what have we got? So Yeah, so we're going to cover bit shifts and bit masks. Then we're going to cover arithmetic shifts versus logical shifts. Then after that, we're going to switch to doing some live coding, and we're going to look at how to implement logic gates in assembly.
All right, cool. So we'll do bit masking, all that sort of stuff. So the reason why we want to do bit masking is because the special registers, it's a confusing term. They're called control registers. They're really very special locations in memory that when you twiddle them, they like turn on IO devices or turn on the LED or like make the board catch fire or whatever. And so we want to like twiddle those bits to make the board do interesting things. So I'm going to suppose at memory address 0x200, there lives a half word of information because I can't be bothered drawing that many bits. So here we go. We have a half word that lives at 0x200. 2, 3, 4, 5, 6, 7, 8. And then I'll put like a purple mark in between so I can tell where it starts. There we go. 2, 3, 4, 5, 6, 7, 8. No, they're not really the same size, but that's okay. So this is bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this refers to an address in memory. And there's a half word or 2 bytes that lives there. So this really lives at 200 and this really lives at, whoops, little endian, got me again. So this is 200, this whole byte. And this is 201, this whole byte. So we store things little endian. And suppose the 6th bit is connected to a light bulb on the board. And if I set a 1 in that bit, it'll turn the light bulb on. So there's a lazy way to do it. I could just load the data from that address and set all the bits to 1. I mean, that'll necessarily set 6 to 1, right? So here's like the bad way to do it. So I load the address 0x200. In reality, these addresses are much larger. I'm just using it for an example. So load into R0 the memory address 200, LDRH, which will load a half word. So we'll load a byte from 200 and a byte from 201 and put that somewhere. So we'll put it in R1. So R1 will now contain OX0000 and then whatever lives in here, this byte, and whatever lives in here in this byte. So I'll put that there in orange. There we go. So maybe I'll just make up some numbers. 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. Alright, so if we decode that into hexadecimal, we're going to have 2, we group the first 4 bits, 0, we group the next 4 bits, 0, 1, 1, 1, that's a 7, and then 1, 1, 1, 1, that's an F. 7. So R1 will now contain OX0000F702. And so the bad way to do it is you just move into R1 OXFFFF, which I don't think you can load a constant that large, so I'll use an LDR. Load into R1 this big number, and then store it back. So store R1 into R0, which will set all the bits to 1, and it will turn my light bulb on. Well, I mean, that might work, but the problem is it also changes these other bits too, and that might be bad, right? Let's suppose bit 7 had like a pile of like dynamite hooked to it that blows up the dev board. I probably don't want to turn that one on as well, right? So here's my dynamite. And it's hooked to pin 7. I probably don't want to like accidentally flick that one and blow up the dev board, right? I probably only want to turn on bit 6 on. So this is the bad way to do it. So you know, don't do that. So put a big, you know, bad. And then the way we want to do it is we want to change only that bit. So let's see the good way to do it. So we load the address like we did before. R0 OX200. Load the half word, LDRH R1 R0. So R1 now contains all this information. If I want to flick just this little bit here to a 1, what I can do is I can do a logical OR. And let's see why. So if we take this whole bit pattern, so let's move the addresses out of the way, and I did a logical OR with this new bit pattern, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. I'll do the 1 in the different colors so you can see it. 0, 0, 0, 0, 0, 0. Okay. When you do a logical OR with a 0, the result is unchanged. And that's because OR satisfies the law x, where x is anything. Logical OR 0 is equal to x. 0 or 0 is 0. 1 or 0 is 1. So logical ORing with a 0 leaves the result unchanged. Logical ORing with a 1 sets the result to 1. Because 0 or 1 is 1. 1 or 1 is 1. So we can logical OR with a bunch of zeros everywhere and a single 1. What that will do, 1 or 0 is 1, 1 or 0 is 1. So it will leave all these bits unchanged, except this bit here gets flicked to a 1, and then all the rest stays the same. And there we go. And so thankfully this time the dynamite bit didn't get flicked on, and my dev board lives to run code for another day.
Well, so we had a question from the chat.
Mm-hmm.
Can you load it as a half? Can you load it as a half word when the data is inputted as a word?
So if you load a half word and the data inputted as a word, you'll just steal the top half. So I'll finish this example and then I'll answer that question. So what were we doing? Okay, load from R0 into R1. Then we can logical OR R1 with the number 10000000 in binary. So I guess you could write that as 0B 10000000. That's kind of yucky, right? There's a whole bunch of zeros. Thankfully, there's a nicer way to do it. This bit pattern is just a 1 logically shifted left. We can actually write that as the literal itself, which is very nice. So if I write 1 shifted across by 1, 2, 3, 4, 5, 6 places, this number here will automatically turn into 0B1 and then 6 zeros. So now I don't have to keep track of how many places to shift. I just write 6 and the dev board does all the hard work. I've done the logical OR, store the result back. Store R1 where R0 lives, and then this bit we flick to a 1, the light bulb will turn on, the dynamite won't explode. Alright, so that's how we flick a particular bit to a 1. If we want to flick a particular bit to a 0, so this is bit set, because set means to turn on, clear means to turn off. So I'll go through an example of clear. Good, clear. So my light bulb's turned on, so let me change this bit to a 1. And suppose I want to turn the light bulb back off again. I could just load zeros everywhere, but that might do something else bad. Maybe there's like, I don't know, a different set of dynamite here. Or maybe there's like a, I don't know, I'm trying to come up with like a silly example. Here's John, and there's a big weight.
Oh no.
And there's an electromagnet holding the weight from falling that's like hooked to this bit. So if I set everything to 0, the big 1-ton weight will squish John, and then John won't be able to teach anymore. That's no good.
Don't crush me, you might fail the course.
Yeah, so we want to turn the light bulb off, but if I set everything to 0, the dynamite won't explode, but then John will get squished. So we want to only flick this bit back down to a 0. So the way I can flick bits to a 0, I can use another identity. So this is the identity for logical OR. We'll look at the identities for logical AND. So logical AND satisfies 2 identities. X and 1 is 1. 0 and 1, well, that's a lie. I've gone and fibbed. X and 1 is X. Yeah. 0 and 1 is 0. 1 and 1 is 1. So logical ANDing with 1 changes nothing. And when you AND with a 0, you get 0. 0 and 0 is 0. 1 and 0 is 0. So we can do the same thing we did before, but it's...
Help write us a truth table.
Oh, sorry?
Just do like...
Oh, yep, sure, do a quick truth table. So x, y, x and y, 0, 0, 0, 1.
Just write a
Yeah,
column
yeah.
once.
Okay, all right. 0, 0, 0, 0, 1. So we can see here, when I logical AND with a 1, which I'm doing here, the y is left unchanged. It's just copied across essentially. When I logical AND with a 0, then the result gets set to a 0. So whatever the result was on the input, it gets totally ignored and the output is a 0. And you can imagine a similar truth table for OR, which I probably should have done, and you know what, I in fact will do. X, Y, X, or Y. 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. So when we logical OR with a 0, the result just gets copied across. When I logical OR with a 1, we put the result in the bin and set the output to a 1. So when we want to clear a bit, I logical AND with this bit pattern. 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1. So, and this is now an AND. So when I do the logical OR, all the bits that I'm ANDing with a 1 stay the same. So 1, 1, 1, 1, 0, 1, 1, 1. 1, 1 and 0 is 0, so this bit gets flicked to a 0. And then everything else stays the same. 0, 0, 0, 0, 1, 0. So now the light bulb is turned off, the dynamite is not exploded, and John is safe from being squished.
Hurrah!
Now the problem is this bit pattern here is very unwieldy, right? What is that as a number? Geez, I don't know, something yuck. But it's the negation of something simple. This number here is the same as this number from before, 1, 0, 0, 0, 0, 0, 0, if you negate the result. So thankfully there's an instruction that does the negation for us called BIC. The BIC instruction, you give it 3 registers, and what it does, takes the first register, logically ANDs it with the negation of the second register, and stores the result back to the third register. So R1, logical AND the negation of R2, store the results in R0. So this makes life really easy for me, because then I just got to remember this number here. This number here is just 1 shifted left by 6. So we'll move our truth table out of the way. This is the same as the negation of 1 left shifted by 6. So if I want to take this data and flip the 6th bit to a 0, that's super easy. I can use my new instruction BIC to help me. So what I will do is I will load the data, load the address. So LDR R0, I forgot what I called it after all that. Data.
Yeah.
I forgot the label of what the data was. Oh, that's right, OX200. Yeah. OX200. And then we load a half word, because it's 16 bits, into R1 from where R0 points. I then do a bit clear, R1 with 1 left shifted by 6, which will set the 6th bit of this register to a 0, and then I can store it back. So store the half word, R1, back where R0 points. Thankfully, you can set more than just 1 bit at once if you use more complicated patterns. So for example, if I wanted to set both of the lower bits to 1, I want to logically OR with 3. And why is that? So let's have a look. So if I've got some pattern, so I'm like, suppose I got some really complicated pattern. So we're working in 8-bit because I can't be bothered writing out lots of bits. 1, 1, 0, 1, 0, 1, 1, 0. And suppose the result I want is 1, and then I'll put pink where it's changed. 0, 0. So I want to 0 these 2 bits. And I want to turn on these 2 bits. 1, 1, 1, 1. Okay. if I want to change this bit pattern into this bit pattern, I got to do two operations at once. I got to logically AND to set bits to 0, and I got to logically OR to set bits to 1. So the first thing I'm going to do is a logical OR. So what do I want? I want these bits to be high. So I will logically OR with this bit pattern. And the result will be 1, 1, 0, 1, 1, 1, 1, 1. And then I want to set these two bits to low. So I will bit clear with 0, 1, 0, 1, 0, 0, 0, 0. Maybe it's a little bit clear to see that as an AND, actually. So I'll write it as an AND. Logical AND with 1s where we want unchanged, 0s where we want flick to 0. So put 2 zeros here, and 1s everywhere else. Yes, John?
Have you made a boo-boo?
Let me just draw this nice and clear. I don't think I've made a boo-boo.
So what are you doing? You clearing? Or
1, 0, 0, 1, 1, 1, 1, 1. So I want to change this pattern into this pattern. So logically OR to turn these two bits on. And then I logically AND to turn these two bits off. Maybe I'll put them in different colors. Colors are good. I think that's right.
Yeah, should be okay. Yeah.
And then so what does that look like in code? So if we we'll assume.
Oh, so you've set the 0th and the 3rd bit, and then you've cleared the 5th and 7th bit.
Yes.
Okay, all right, yeah, and you've just done that with an OR and an AND.
That's right.
Okay.
So if we assume our 0 contains the original pattern, 1, 1, 0, 1, 0, 1, 1, 0, the code I have to execute is I do the logical OR. So OR R0 with this number here. So 0B 1001. And then I bit clear R0 with the negation of this number here, which is 0, 1, 0, 1, 0, 0, 0, 0. Sometimes doing a bit clear is easier if you're only trying to clear a single bit. If you're trying to clear lots of bits, maybe it's more useful to do it as an AND. A BIC is just an AND with a negation on top. So maybe it's more clear if I write this as an AND. So AND R0 with 0B 1, 0, 1, 0, 1, 1, 1, 1. And then the end result, R0 contains 1, 0, 1, 0, 1, 1, 1, 1.
Dave, I think I've made a boo-boo.
Oh, what have I done?
When's this bit getting set?
0 or 1. Whoopsies.
Yeah, so wouldn't you want that to be up here? Or are you even trying to change that bit?
I don't believe so. Yeah, no, I've just marked that. Whoops.
Thank you, person in the chat.
Yeah. Whoops.
Mysterious U number.
Yeah. 1, 1, 0, 1. I want to clear these two bits, so this becomes a 0. Yeah.
Yeah, okay, there you go.
Yeah, definitely that was a boo-boo.
Thank you.
I
We're done with this example?
believe so, yes.
Do we want to take like a 2-minute break because we've been going for an hour just to have a quick drinks break?
Yeah, sure.
Okay, so how about right, it's 1907, it's 7 past 7, and let's say we'll be back at 10 past 7 to continue. So next up we'll look at what an arithmetic shift versus a logical shift is. So we'll do that next. So we'll be back in 2 minutes. I'm going to go grab a cup of tea.
Alright. You want to kill the microphone?
I can't do that trivially, so
Alright, sure. We'll just don't say silly things. No, no.
Oh boy, I'm back and I'm not even late. Hooray! Anyone? Cool. Okay, wonderful. Oh, we still have 26 people. We're doing good. This is like real pro streaming hours. Oh. Okay. David's still eating pizza. So, oh, excuse me. Let me flick this to OBS so I can see what I'm doing. Right, nice. Okay. Squish. What do you want to do, Dave?
What's that?
ASR versus LSR.
Oh yeah, sure, that's an easy one, I can do that.
Okay, alright.
Here's your food.
Jump in. Yep.
Alright, back I am.
Pizza Man Dave has delivered.
Alright, what are we doing?
So, arithmetic shift versus logical shift, right?
Yep, sure thing. I don't believe this will probably come up in the course, but I'm happy to do it anyway. So, logical shift versus arithmetic. So, let's suppose we're working in 8-bit land because I'm lazy. I've got some bit pattern here. 1, 0, 1, 0, 1, 1, 1, 1. When I logically shift to the left, it just bumps everything over, fills in zeros on the right. So this 1 falls off into oblivion. 0, 1, 0, 1, 1, 1, 1, 0. So we just bump everything across. And then a 0 appears to fill this blank spot. Cool, that's what logical shift left is. Arithmetic left shift is literally the same thing. So no difference there. The difference appears when we shift right. So logical shift to right and arithmetic shift to right, they sometimes differ depending if the number is negative or not. So I'll do an example for negative numbers and for positive numbers. And I'm only shifting by 1 bit here. So for logical shift to right with a positive number, 0, 1, 0, 0, 1, 1, 1, 1. All I do is I shift to the right and I bump over the 0 as well. So we have 0, 1, 0, 0, 1, 1, 1. This 1 falls off into oblivion. Shift everything right. And then we get a 0 to fill the gap. When we do arithmetic shift right, we steal the new bit from the sign bit. So if I do an arithmetic shift right on a positive number, I mean the end result is the same. So this 0 is copied down to both places. And then everything else is shifted right. And the 1 falls off the end of the world. 0, 0, 1, 0, 0, 1, 1, 1. And then the 1 goes away. If we arithmetic shift right on a negative number, which I will do up here. So negative numbers have a leading sign bit. 1, 1, 0, 0, 1, 1, 0, 0. I shift right. Then the 1's copied down as well. So 1, 1, and then I read the rest off. So 1, 0, 0, 1, 1, 0, then the 0 falls away. Why is this useful? Well, we know when we do logical shifts, it's the same effect as multiplying. But if I take a negative number and logically shift it to the right, it's no longer a negative number. And when you take a negative number, multiply it by a positive number, which was what shifting does, the result should also be negative. Now, when you do an arithmetic shift to the right, I guess that's dividing by 2, right? Shift to the right is divide by 2. And the problem is it won't respect the sign bit. So when you do an arithmetic shift and you divide by 2, the result is still indeed negative. So if we have, I don't know, mov into R0 negative 8, and we do an arithmetic shift right, which I can't remember the command for. I assume it's ASR.
It is ASR.
It is ASR? It is indeed. ASR R0 by 1. Then the end result is that R0 will contain negative 4, which is what you'd hope, right? If you take negative 8 and you divide it by 2, you get negative 4. But if you did a logical shift, you'd get completely the wrong answer. So let's see what happens if we logical right shift a number that's negative, and we'll see what silly answer we get. And again, this is an 8-bit land. your mileage may vary if you're in 32-bit land, which you are. So 8-bit land, -8. How do I write a -8? Well, I write an 8. 0, 0, 0, 0, 1, 0, 0, 0, 1, 2, 4, 8. Yep, so that's 8. Flip all the bits and add 1. So +1, 0, carry 1, 0, carry 1, 0, carry 1. 1 plus 0 is 1, 1, 1, 1, 1. So this thing here is my -8. 1, 1, 1, 1, 1, 0, 0, 0. If I logically shift right, 0, 1, so logical shift by 1, 0, 1, 1, 1, 1, 1, 0, 0. And then I convert this backwards. So subtract, so flip all the bits and add 1. So to undo that operation, I'll subtract 1 and flip all the bits. So we subtract 1 to get our decimal number back. 0 from 1 I can't do. We go to the next place. 0 from 1 I can't do. So I borrow a 0 copied here. Borrow a 1 copied here. 10 take 1, 0, 1 take 0, 0, 0, 0, 1, 1, 0. So that's subtracting. No, I've stuffed that up actually. Let's do that again. It appears I can't subtract binary numbers terribly well. That's no good. 1, 1, 1, 1, 1, 0, 0. Subtract 1 from this. So -1 should be 0, 1, 1, 1, 1, 0, 1, 1. Because this is 3, add 1 to get 4. Yeah, okay, so that's the correct subtraction. And then flip all the bits. 1, 0, 0, 0, 0, 1, 0, 0. What number does this represent? Something silly. 1, 2, 4, 8, 16, 32, 64, 128. 128 plus 4 is 132. So I took -8 and I right shifted by 1 and got 132. Well, that's not dividing by 2. That's nonsense, right? So the reason why arithmetic shift rights are useful is if you want to emulate a division by 2, but on negative numbers, it does the correct thing that it should. Cool. All right. There you go.
So maybe as well, just do a 4-bit example of why you want to use LSR when you're dealing with unsigned. Oh
yeah, that's a good example.
And then one other quick question.
Well, no. LSR and ASR do the same thing on unsigned numbers, right? Because it just copies the 0 down.
Oh, but like if you've got an unsigned number where the most significant bit is 1, then it will
yeah. Now I understand what you mean. Yes, of course.
Yeah.
So.
And then I've got one other question for you after that.
Yeah. Okay, no, I get you now.
I'll just do it in 4 bits.
Yeah, sure. We're working 4-bit land. So what's a relatively large number to divide by? 14 is kind of big.
Oh, just do 1, 0, 0, 0. That's a real simple example.
That's right. So 14 is equal to 8 plus 4, 9, 10, 11, 12, 13, 14. So 1, 1, 1, 0. Okay, that's 14. If we logical shift right by 1, the new bit pattern is 0, 1, 1, 1. 1 plus 2 plus 4 is 7. And 14 divided by 2 is equal to 7. So that makes sense. But if I do an arithmetic shift in this case, I get silly answers. So 14 is 1, 1, 1, 0. If I ASR by 1, copy the first bit down, shift the rest over. We get 1, 1, 1, 1, which is 15. 14 divided by 2 doesn't equal 15. So basically, if you're doing shifts for the purpose... Oops, I got rid of my logical up here. Logical. If you're doing shifts for the purpose of multiplying or dividing by 2, logical shift right is for dividing by 2 unsigned numbers, and arithmetic shift right is for dividing by 2 signed numbers because it preserves the signed bit. Right, cool.
And the last question was to do with shifts. So on the cheat sheet, if it says carry equals last shifted out, so maybe just do a quick example.
Oh, that's probably going to be some silly rotate instruction, right?
That's for any of the shifts, I think.
Carry equals last shifted out. Oh, okay, cool.
I think, is that just for left shifts or is that also for right shifts?
Let me have a look. So it's for LSR,
And
last shifted out.
it's for any of them.
Oh, so it looks like... Okay, so when I said this falls off the end of the world into oblivion, I actually lied. It actually goes into the carry bit slot.
Yeah.
Alright, so I guess I'll do a quick example
So
of that.
I'll do one where you shift by 1 and do one where you shift by lots of numbers.
Yeah, sure. Alright, so we're going to work in 8-bit land because I'm lazy. Arithmetic. So in 8-bit land, I've got some number. 10110110. I'll execute a left shift by 1. So here's my number, and I'll draw little columns so I don't get lost. So each bit gets shifted to the left. So 0, 1, 1, 0, 1, 1, 0. And this last one goes into the carry slot. And then a 0 gets introduced here on the end. But if we shift by lots of things, it's a little bit more complicated. So the carry bit contains the last bit shifted out. So let's do like a left shift by 3. So the same number, 1011 0110, LSL by 3. So rubbish, 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 and then we start copying them over. So we have a 0, we have a 1, 1, 0, 1, and then these 3 go in the bin. 1, 0, 1, they all go in the bin. The last thing shifted out, I guess, would that be this one or would that be that one? I think it's this one.
It's this one, yeah.
It's this one, yeah.
So you can think about the last thing shift out, sort of, say you do a left shift left by 3 bits. You can also do that by left shifting by 1 bit 3 times. So sort of do a thing like that. If you were to do a left shift by 1 bit 3 times, what would the last bit shifted out be? In this case, it would be this bit. So that's what I mean by the last bit shifted out. The last bit that got shifted off into oblivion. Well, actually, if we're setting flags, it gets put into carry. So specifically, make sure these are LSLS as well. Because we are setting the carry flag.
LSLS
Yeah,
to set the flags. Otherwise, it won't set the flags. Why bother with all this rubbish? Why not just let the bit fall off the end of the world? Well, suppose you got a 128-bit number stored in memory, and you wanted to logical shift that entire number. You have to load it 32 bits at a time, and then you actually want to know what the bit is on the end, because you want to shift that into the next number. And I'm sure there's a command that like loads. Where are we? So LSL filled with zeros. And we can see here, raw and RRX, these commands here will load from the carry. So rotate's a little bit funny. I mean, it does exactly what's called on the tin. When you do a rotate, so I have 1, 0, 1, 1, 0, 1, 1, 0. So I shift everything to the left, so we'll do like a right. Does this even have left rotates?
Yes, it does. LSLs.
LSL.
Oh, sorry, no, there is no rotate left.
There is no rotate left?
No.
Why on earth is that?
Because you can rotate right to do a rotate left.
Ah, of course you can.
Yeah.
Ah, clever. Right. So I'll give an example of what the thing I just myself understood 5 seconds ago. So we rotate right. So it's like a shift to the right. So we'll do a rotate right by 1 bit. So we're going to have something on here. 1, 0, 1, 1, 0, 1, 1. And then the 0 goes all the way to the start. And put the 0 here. And so I thought to myself, well, there's no rotate left. That's not good. But a rotate right is a rotate left by a different amount. If I'm in 8-bit land and I rotate right by 1, that's the same thing as rotating left by 7. Because you just rotate all the way around.
Yeah.
So that's why we don't actually need this command. Just emulate it with rotate right.
Yeah.
So if you rotate right by -1, that's the same as rotating left, which there isn't a command for that, by 7. Alright, but
yeah,
that's
cool,
neat. I learned a thing today.
Yeah, cool.
What else we got, John?
Sorry, I'm just answering a question in the chat about arithmetic and logical shifts. So, when we're talking about how shifts do divisions, they divide by powers of 2. Maybe you want to
Yeah.
something on the whiteboard?
So if we're in 8-bit land again, I like 8-bit land.
I'm just talking about like straight mathematical equations here.
Oh, okay,
So,
sure.
like,
Yeah, so if
you-
I have x and I left shift by n, that's the same thing as taking x and multiplying it by 2 to the n.
Yeah.
And when I have x and I shift right by n, that's the same thing as taking x and dividing it by 2 to the n and then rounding down if there's like fractional numbers. So for example, if I take 3, left shifted by 2, that's going to be the same as 3 times 2 to the 2, which is 3 by 4, which is 12. If I take 7 and right shift by 1, that's going to be the same as 7 on 2, and then flooring this result. This thing just means rounding down, sometimes called floor. 7 on 2, well, 7 divided by 2 is 3 and a bit, and the bit goes in the bin, so we end up with 3. Cool.
Yep, cool. Okay.
This used to be super useful in the 80s when you were using your Ramesh supercomputer. You had to look at the sample questions. This used to be really useful in like the late 70s and early 80s when computers didn't have multiplication division. It was just too hard to draw the circuits for it. So we ended up just emulating the result with shifts and adds. And so you can do all sorts of cheeky stuff, whereas if you don't want to multiply by power 2, well, 5 times x is 4 times x plus x. And then 4 times the number is 2 shifts. Shift by 2 and then add x. So you could do like really cheeky things to write any multiplication as like a combination of adds and shifts. Because not too long ago, multiplication was just, relatively long ago, like 30 years ago, multiplication was too difficult to do in hardware, so we'd do it with adds and shifts. But now, your dev board can multiply in a single instruction using the mul instruction, so this information is a little bit not so useful so more. But it's good to keep in the back of your mind. This is one way to interpret what a shift is doing.
So sometimes it's very useful to know about this if you're doing like a cheeky add and a multiply, for example, by using the barrel shifter with an add instruction. If you remember one of the group question examples, mul by 7, we didn't actually use a mul instruction to do that fast multiply by 7. We used a shift in conjunction with a subtraction or something. So it's good to have in the back of your mind at least how these shifts work. Especially if you get an exam question on shifts, then it's obviously very important to know what they do.
Yeah.
That might have been a small hint. Okay, cool. So, Dave, if you want to jump back on question time, I'm going to do some live coding now.
Yep, sure. So I'll hop up.
Okay. Cool. Nice, cool. You can see me. Hello, everyone. Welcome to the live stream. Wonderful. So, what are we going to do? Okay, so we had a question on doing logic in assembly. So standard logic gates. Dave, if they elaborate on what gates they were talking about in the chat, let me know. So what are our standard gates? So we have not, and, or, XOR. Then we have not ors and not ands. Okay, actually I might switch back to the whiteboard very quickly and just draw all those down. Document camera mode, fade, bing bong. Grab a whiteboard marker.
Aggressive erasing action. Wonderful. And where's the marker? Not the brown one. Okay, we'll use the brown marker. Screw it. Cool, and
And what are you doing?
I'm just drawing some gates.
Oh, okay, yep. Sure.
Okay.
I will jump back over to this machine so I have the nice clacky keyboard to tap on.
Cool, and we're in frame.
And the squeaky
So,
chair.
let's draw some gates here. Right, so this gate is a not. We'll draw this gate is an and.
Probably also go through like bubbles on the input, bubbles
Yep.
on the output.
This gate is an or. So the difference between an or and an ands are kind of fat and have a flat line here. Ors are kind of skinny and have a curved line here.
And they're pointy, yep.
And finally we'll do an XOR. Now, I'll also draw the symbols for these if you're writing it in like a logical expression. So not is either that little boy or a bar over whatever you're knotting. And looks like an A, or looks like a bucket. And XOR is a circle with a cross drawn through it. Now, so what are actually all these gates? So AND, OR, and XOR. Now, not. This is an easy way to explain what these little bubbles on the output are. When we're talking logic, a triangle is actually a nothing gate. The triangle itself does nothing. The reason why we draw a not gate like this is that we're actually more interested in the bubble on the output. So if we have a bubble on the output or the input of a gate, it means not. So say to draw a not AND, I would do this. So a not AND is just an AND gate with a bubble on the end. This is also equivalent to me drawing...
Can you move it a bit out of frame, John? Just can you move it a bit closer?
Oh,
that's what you're seeing?
Yeah, oh boy. Yeah, okay. So if I angle it this way, cool, okay. Sorry. If we look down here, so AND with a bubble on the output is a not AND. Now, AND with the output fed straight into a not is also a not AND. So in a way, we can kind of think of these bubbles like we're just drawing a little not gate there. Cool, okay. So I'll switch back to the live coding now. Dave, can you switch me back to... and also get me away?
Yeah, I don't know how to do that, so you take over. I'll jump back on this machine.
Okay, desktop capture. Switch. Coolio. Alright. Oh boy, streamception. Watch out. Alright, cool, wonderful. So let's do some of these in assembly. Anyone talking in the chat, asking questions? No? Cool.
I'll wait for the thing to load, and then I'll tell you.
I'll check the chat myself quickly. Wonderful, okay. Let's do these gates. Now, if we look at our cheat sheet, I'll just get it up real quick. You may notice that there isn't actually a not instruction in here. Now, we can kind of do this in a bit of a cheeky way instead, using an exclusive OR. We grab this here whiteboard and draw a quick little truth table on it. X, Y, and X, E, or Y. Oh, shut up, phone. Oh my god, excuse me. Very professional. Do not disturb for forever. Goodbye. Okay. 0, 1, 0, 1, 1. I'll do 0, 0, and 1, 1. Then alright. Sorry for the delay here. Alright, let's put this in OBS mode. Cool, so if I bring this up here, camera, right there. Cool, so if we look at this truth table here, if we XOR by 1, then we can see that X is being flipped. So if we keep Y as a constant 1, and we XOR it with X, we can see that this is actually behaving kind of like a not, because our 0 over here is turning into a 1, and our 1 over here is turning to a 0. So although we don't have a not instruction, we can emulate one by just exclusive ORing or XORing with a 1. Okay, so let's jump back on the computer now and have a look at what that'll look like in assembly. Wonderful, more streamception. Okay, so we have our not here. So what I'll do for all these is we'll just assume so we're operating on the 0th bit of register 0. So we'll move 1 into R0. Now we'll EOR R0 with 0B1. Okay, so 1 exclusive OR with 1 is going to result in a 0, so we'll end up with 0 here. If this was a 0, exclusive OR with 1, we would get a 1. So we've implemented a NOT using exclusive OR. Now to do AND, okay. AND is nice and easy. We just AND R0 and R1. So the easy way to do logic in kind of a gates way is just pretend all your registers only have 1 bit, which is the the least significant or 0th bit, and just sort of work that way, right? So we don't have to worry about all the other bits if we're doing kind of digital like a logic circuits. We sort of just pretend registers are only 1 bit, so we can treat them like a wire in a logic diagram. Alright, so yeah, and we can just do like that. So that's the same as an AND gate. So R2 equals R0 and R1. Actually, I'll write some comments. Keep everything nice and clear. R0 equals not R0. Now OR is also nice and easy. XOR, well, we just looked at what that was, so no surprises here. R2 equals R0 or R1. Not OR, so what we'll do here is we'll take this and then we'll EOR R2 to everyone. So I just explained on the whiteboard earlier how we can sort of do all of our not, like our not ANDs and our not ORs by putting a bubble on the output of the gate. And that's also equivalent to just wiring the gate straight to a NOT. So what we're going to do here is we're going to do an OR, and then we're going to immediately invert or NOT that OR. So that's what this is doing here. Okay, so I'm hoping that's fairly clear what we're doing here. So we're saying R2 is not R2, and we just set R2 to be this. So what we're actually saying is R2 is not R0 or R1. So that does our not OR, and we'll now do a very similar thing for NAND. So similar, I'll actually just copy paste everything.
Do you want to crank the font up a bit?
Yeah, I can crank the font up, just give me a minute. And we'll put an AND over here. Okay, coolio. Oh, my nose is so itchy.
File preferences. Yeah, crank up a bit. Just a bit small.
Beaten. Oh, g'day. Cool. All right, here we go. That's nice and big on my screen. Okay. So yeah, we've done our NOT over here. Let's just get rid of small. We don't need to worry about it. Alright, so here we go. So I hope this has answered your question fairly thoroughly. So these are all of our kind of standard gates. I don't think you can expect to see too many other gates other than these. So yeah, we've got our NOT here, which we've done with XOR. We've got ANDs, ORs, and XORs, and then not ORs and not ANDs. Cool. Okay. What was next? Next on my list. So we've done logic and assembly. Bit shifts, as and ways, LDI. Oh, okay. So let's have a quick look at the different kind of indexing in loads and stores. So I'll put some junk in my .data. Let's think of something more inventive. Let's not think of anything more inventive. Okay. Jump into our cheat sheet now. Okay, so we have a few different load and store options in our cheat sheet. We have offset, which I'm hoping most of you will know what that does now. we have pre-offset and we have post-offset. So let's have a look at what these different things do, and we'll debug and see how they all work. Okay, so sometimes it's really easy to forget which syntax is which, so just be careful when you write these. So what we're going to do is we're going to load to R0 the address of our sum data label. So we're loading the address of some data, which is going to be the address of the first thing after it. So we're loading the address of this word here. Cool, and now we'll LDR R1 sum, excuse me, R0. Alright. Cool, we have a bucket of different loads here. Okay. Alright, so we have 4 plain loads here. Let's have, so if we go through cheat sheet order, we have offset, pre, and post. Okay, so let's say this is the address of our dead beef word. What if I want to load this word here? Okay, so we can do that with an offset load. I'm hoping most of you are familiar with this. So our dead beef word is going to be 4 bytes long, and we want the word after it, so we'll just add 4 to our address. So we'll offset by 4 bytes. So instead of loading from these 4 bytes, we'll load from the next 4 bytes, which is this word here.
And this makes more sense when you look at it in the memory viewer.
Yeah. Now, we have our pre and post offset. Now, pre and post offset might not make much sense, because when we do an offset, we're just sort of adding these two things together. So what does it mean by pre or post? So what these actually do is not only do they offset, but they then write that offset back into the address register. So this will make more sense in a minute. But okay, so let's say we also want to load this word, but we also want to offset. As in, sorry, we want to write back our offset. And we'll do the same thing here as well, but with post offset syntax. So basically, the difference between these two is how and when they increment. Instead of trying to bubble through an explanation, I'm just going to debug it. Oh, excuse me. Cover. Nice. Okay, so we'll skip through to our code. Wonderful. Memory viewer. Hang on, let me step over and get some goods. Registers. Perfect. Oh, fuck. Oh my god. Platformio, hooray. Don't we all love Platformio? I know you all love Platformio. Platformio is your best friend. 1, 2, 3, 4, 5, 6, 7. And load button. Okay. Right, so we're looking in memory. R0 contains the address of some data, which is going to be the address of our dead beef word, which we have here. We have our second word, 42, here, and we have our third word with 69s here. So let's step over our code and see what happens. So the first load, that should be pretty simple what it's going to do. It's going to load a word from this address. So the address is pointing to this byte, and we're going to load a word. So we'll count up to 1, 2, 3, 4 bytes, and we'll kind of load them in backwards because we're in a little Indian processor. So we'll get DE, AD, BE, EF in R1. Cool. Now, we're going to do the same thing, but we're going to skip ahead 4 bytes because we have a 4 byte offset here. Okay, so that's nice and easy. We've loaded 42. Now, what's this going to do? So earlier I mentioned that these LDRs will write back. So what that means is the keyword here is pre. So the way these work is that we will do this addition here. We'll do R0 plus 4. And then we'll write that back to R0. So R0 will equal R0 plus 4. And then we'll do a load. So in other words, we do this sort of offset addition before we do the load. So I'll step over. So what it's done is it's added 4 to R0, as you can see up here, and then it's done the load. Now, how does that differ to post offset? So post offset does it the other way around. Post offset will load from the address in R0 and then offset. So once again we've added 4 to R0, but we loaded before that. So we've actually loaded the same thing 3 times. Because this time we loaded from an offset of +4 and we didn't write it back. Then we loaded from an offset of +4 and wrote it back after we did the load. And then this time we loaded from that same address and then we added 4 to it after we did the load. So yeah, they're all different ways of just incrementing the address we're loading from. So these two here right back. So this is pre-offset will offset and write back, then load, whereas post-offset will load, then offset plus. Okay, so that's the main difference between our different kinds of loads here. Do we have any questions in here? Wonderful, cool, okay. Cool. So yeah, that's the difference between these. Okay, I hope hope you can wrap your head around that. It's a little bit tricky, but we're there. Cool. My little list of things to work through has been exhausted. Questions from the audience? Anyone?
No, I don't see nothing.
Cool. Is there anything else that we should run through before the exam? Do you reckon?
I think we're pretty much good. Is there anything else in the chat that we haven't done? The problem is when you refresh the page, the chat vanishes, which is really great.
Yeah.
Just move the camera out of the way.
Bloody streamception going on here.
Is it better to do ASR? Well, most of the time when you're doing a shift, you're not interested in what that means in terms of like multiplication or division. You're just interested in like shifting the bits across to like rip out a particular bit pattern or whatever. So yeah, if you're shifting for the purposes of multiplying or dividing, then yes. Otherwise, no. I guess you just use a regular logical shift.
No.
I'd say we could probably call it and then upload this to YouTube or whatever.
Yeah. So I suppose last request from us. Let's go. Let's see if my face cam works. Nice, cool. Oh, nice. Hello. Yeah, there you go, Dave. You can even lean in and say hello to everyone. Oh, Jesus Christ.
Yeah, no, it's too dark. We just tilt that lamp up at something.
Cool. So.
G'day.
G'day. Yeah, I hope you found this live stream helpful. I was actually thinking earlier that maybe what we could do for lab solutions was we could have like a regular live stream that only gets recorded and uploaded to YouTube for the lab solutions. That might be a bit nicer than just having sort of some random bog YouTube video, because that way you can sort of watch along. I don't know. Live streams are good fun.
Well, it depends, right? It might be useful to watch us solve it the way we would solve problems.
Yeah.
I mean, maybe that's useful to watch us struggle with things and watch us make mistakes. You can see in some of the videos I've made, I like goof something up and then I'm like, oh, that's not right. All right, let's go fix that, right? And so by watching us solve problems, maybe that's pedagogically useful.
And yes, that is a Skyrim map on my wall at home. Yes. Yep. Yeah. There's a whole bunch of there's a few posters I had to take down because they weren't really appropriate for doing a course video, unfortunately. But there's plenty of good entertainment in my room. Shall we say? So
I guess we will maybe do this again. No, there's not much point doing it next week because of the break. But maybe after the break we'll start doing this again. Yep. We'll see.
One last thing. Is anyone completely stuck? No idea where to start on the assignment? I can't answer too many assignment questions because I can't just tell you a solution to the assignment. But if you're like really bogged somewhere on the assignment, that might be something we can. I mean, yeah. So
I mean, we could maybe have a Q&A, but most of the answers will be like, I can't comment.
yeah.
I mean, you try, right? Like, ask us. But we can't really say much about the assignment, unfortunately.
Suffice to say, if I expect my Friday. Oh, sorry. I'm not taking the drop in this Friday. Look, if you're in one of my tutes, or really if you're in any of the tutes, you should just ask your tutor. If you're really bogged on the assignment, I think might be a good idea.
It probably wouldn't be appropriate to talk about in the stream. So
sample rate is after TS. Yeah, so the way the sample rate works is that the audio out function will play a sample at the sample rate. Oh, sorry. Next Friday there will be a drop-in lab. There just won't be me there because I'm actually going on a holiday for my birthday. Yeah. So terribly sorry to break your heart, Michael. You won't have me. You'll have one of our other equally good and entertaining tutors. At this rate, it'll. Oh, I have no clue who. But it won't be me, and it won't be David either. Very sorry.
No, unfortunately, I teach a different tutorial during that time. Otherwise, I'd be happy to fill in for John. Sorry.
So I think Murdoch will be there. Benny will probably be there. Benny's really good. And I think we'll probably get Rahul there as well. So there should be 2 or 3 tutors there. So that'll be good footage. Yeah. But yeah, if you have any assignment questions, honestly, just ask your tutor. I expect the Friday drop-in is going to be a bit of a bogged kind of help. My assignment isn't working. I don't know what to do, and unfortunately, we can't answer too many questions because it's a simple assignment. We can't give you the solution to it. So
yeah, at the end of the day, we can help as much as we want with anything that's in the lectures or anything that's in the tutorials. But the assignment is a thing that you have to do yourself. So the only thing I can really do is basically repeat the assignment spec to you, which is most questions students ask in tutorials. I just end up rephrasing the assignment spec, and that tends to guide them to what they want to do. But if it's like, David, why doesn't this work? I'm like, oh, I can't comment, sorry. That's just the way it is, I mean, I have to be fair, right?
Yeah. Okay. But yeah, cool.
Alright, I think you can get enough now, so
good stuff.
possibly see you all next time.
Yeah, hopefully there was a next time. One last final thing before I go. If you like this live stream, the way you can make sure there's more live streams is if you flick a chat to the course reps, flick them a message, communicate in any way that you like, smoke signals if you prefer, to your course reps. So once again, tell your course reps that you like the live streams. That's how we can get more of them. The school gets happy, Ramesh gets happy, everyone's happy, you're all happy, we're happy. Yeah, life is good. Anyway, so I'll upload this into YouTube or Twitch at some point after this. Thank you very much for coming. See you next time. Ta-ta. Stop streaming. Goodbye.